As the title suggests, we're going to be talking about modeling HVAC and environmental flows using real-time CFD, specifically M-Star on GPUs. This is a different application than we've spoken about throughout the last year, which typically focus on process simulation or process modeling. One thing I hope you'll see here is how it's all the same thing, right? It's all the same physics governing these transport processes. It's the same model setup in general. And with a few modifications, we can completely recast what might have been used to simulate a bioreactor into a pretty cool framework for modeling creature comforts, airflow, room turnover, particle counts, etc. And use this tool not just to study processes, but also the facilities and rooms which these processes are developed. And you'll see here kind of some breadcrumbs that I think I've kind of left over the past few months that speak to this kind of parallel and adjacent space. So again, we're talking about HVAC and CFD at something of a larger scale. And here is an illustration of some people working in a lab space or storage space, going about pushing their carts and going about emitting particles, as people have a habit of doing even when they're gowned. We've got some vents here. I'm not showing the airflow. I'm just showing the effect of that air on the particle transport. As people kind of hang out and chit chat about the game last night. But a couple of things to note here. We want to look at things like, again, ventilation, recovery time, particle counts, heating and cooling, we'll get to momentarily. And again, applications and relevant focus would be things like a facility designer. It would be relevant to healthcare settings, operating room settings, clean room operation, etc. The interior comfort, as I mentioned, whether this be in a room or a cabin of a vehicle. Foundationally, we want to understand, again, how air moves through these facilities, how particles accumulate inside these facilities, and how comfortable these facilities might be. One unique thing here is that these facilities can be large, right? They can be, their characteristic length scale may be measured on the order of, several tens to hundreds of meters, right? And that's very different from a lot of these smaller systems we're used to studying. So I do want to touch on like how turbulence scales and how you consider systems that are big, where the voxel size might be, I don't know, 10 centimeters compared to the sub-millimeter we frequently see in more process applications. I always say this. I always start with this because it's such an important point. I think it's a novel point. All of this made possible advances in GPU simulation, and we focus on GPU evaluation. Just because we have to do focus in the room, I'll emphasize this again. M-Star runs entirely on GPUs, and the important advances it presents in terms of speed and fidelity are made possible by GPU-based computing. A GPU is different from a CPU. Every computer is a CPU. The CPU runs operating systems. CPU can read a keyboard and send something to a printer. A CPU can browse the web and interpret how a mouse should move. But a CPU tends to present a low compute density. So again, a CPU might have 4, 8, 12 cores, as it were, and some cache. But 4, 8, 12 cores isn't a lot compared to other architectures, e.g. GPUs. Furthermore, CPUs have a slow bandwidth. It takes time for them to talk through the PCI bus in the computer and access RAM, which is a stick that's plugged into the motherboard. So again, they have their general, they're functional, they're useful, but they're not really tailored compared to a GPU for high performance computing. A GPU is different. A GPU will have thousands of CUDA cores in one piece of architecture, and all the memory it needs is stored locally, which gives them an incredibly high memory bandwidth, which means they can shovel the data quickly, and the vast number of CUDA cores, which might be several thousands or tens of thousands compared to the 4, 8, or 12 we get at a CPU, offer an order of magnitude improvement in just raw speed. And so running on GPUs, you can snap into your motherboard, as it were, can present multiple orders of magnitude improvement in speed, right? And I don't want you to hear, oh, it's 10 to 20% faster. No, it's hundreds of times faster when you run on a GPU. A similar physics that would be run on a CPU, as it were. This changes how we approach simulation. Again, I give this slide quite a bit. But foundationally, for a lot of simulators, and especially in the HVAC space, we rely heavily on correlation, as it were. When we're able to run simulations this fast and with this fidelity, it allows us to model physics explicitly. We're going to see that today. We're going to compare it to some good literature examples, which show a steady state RANS picture, and be able to turn that into an actual time-accurate three-dimensional simulation of the heating and cooling process, where we're far beyond the temperatures are going to be red here and blue here and green here in the room. to the actual, here's the time evolution of the temperature. Here's what the person's feeling as the air comes down on them. And here's how long it takes them to recover at this particular spot in the room to recover some target temperature, what sort of fluctuations it'll see. So again, the salient point is driving closer towards the actual transport physics, which makes these models general, as it were. Again, my last kind of introduction overview slide. And here's, we'll speak to the system later on. We're modeling this physics in a time-accurate manner. Here's kind of a little lab space. We have some sort of leak. Eventually, there's going to be a sensor here that detects that gas and then purges the room or attempts to purge the room. This isn't a great purge because as part of this purge, we're just kind of mixing the bad gas everywhere. We can do a much more intelligent purge by selectively turning on some of the inlets and outlets, as it were. But foundationally, this is in play now. This idea of time-accurate, three-dimensional, inline controlled, multi-phase simulation, multi-phase species simulation, tracking concentrations, tracking particles, that's in play. And it's not just in play, but it's routine, as it were. And in fact, for many of the simulations, we can beat real time, which is kind of neat to understand a facility design. Okay, I want to talk about, touch on this point about scale. I should have had a transition slide here, so I apologize about transition. But this is kind of an unsaid fact that we need to speak to. In most of our work, our systems are lab, pilot, or production scale, measured in, 1, 10, 100, thousands, maybe tens of thousands of liters of fluid, right? Maybe 10 cubic meters at best. That's great. That's useful, but that's also, I'd say, compared to a facility, small scale. Again, a vessel fits inside a much, much larger operating facility, as it were. And so we might think to ourselves, well, the turbine mechanics that are happening in the small scale are going to be very different from the mechanics happening at this large scale. But folks, that's not true, right? Turbinate flows have this beautiful self-similarity anchored to a few key intrinsic length scales, as it were. And so if we have a turbinate system, yes, and we plot, say, the spectral energy density, this is the amount of energy contained in an eddy, and this is the eddy size. This is wave number. This is a length scale. And so over here, we have a Kolmogorov length scale, the smallest eddy we have inside the system. Here are larger integral scale eddies, which contain a lot of the energy. And obviously, for a given system, as we increase the amount of energy, think of like the impeller speed or the inlet flow rate, as it were, the integral of this curve goes up because there's more total energy inside the system, of course. But if we divide this by the total energy, we get this beautiful self-similar curve that describes how energy will be distributed from this inertial subrange down to the viscous regime. And that's where, Kolmogorov and the Taylor start to win. That is all the turbulent structure. Integral scale is different, but in the subgrid dynamics down to the, I shouldn't say subgrid, I should say in the limit of the isotropic turbulence, it converges down to a self-similar solution. Very similar to what we see near a wall, where we have the law of the wall and turbulent flows respecting the similar Y plus relationship. We see a similar structure in free turbulence, where free turbulence collapses down once you get below this Taylor scale to this well-designed, well-predicted, well-understood viscous dumpster, where the eddies are quickly thermalized down to the Kolmogorov range. And so there are a few key characteristic length scales that inform the shape of this distribution, but they're intrinsic. Said again, the Kolmogorov length scale is a function of the Reynolds number alone, and then the scale of the vessel. But it's not a function of, say, the shape of the room, unless that shape informs the Reynolds number. Likewise, the Taylor scale links directly to the Reynolds number. The integral scale will be a function of topology, as it were, but those are the things we're going to resolve the best explicitly. It's here we're concerned about as the grid size gets bigger, but importantly, because this grid size scales with length scale, we can achieve a practical LAS simulation, even large scales. I'll speak to it like this. Take an old impeller, take a simple agitated vessel here. I purposely am not telling you what the length scale of the system is, because importantly, it doesn't matter. Like if this were 1 or 10 meters in diameter, provided the Reynolds numbers are self-similar. Importantly, if we have large eddies, which inform the bulk transport, that's this region out here, they're going to be highly anisotropic, and yes, their shape and their structure will be informed by the size and shape of the room or the vessel or the bed over which the air is flowing. When we get down to the inertial and dissipation ranges, however, which are characterized by the Taylor and the Kolmogorov scale, these become functions of just the Reynolds number. Said again, if we know the Reynolds number, The flow isn't looking over its shoulder to understand, oh, I'm in a big vessel, I better decay it this way, or I'm in a small vessel, I better anticipate this way. Instead, as a function of the system Reynolds number, we can inform what sort of Taylor length scale, Taylor and Kolmogorov length scale we'll see, which again, because the Reynolds number involves a length scale in our system, it's going to scale with system scale. I'll say it again. Here's a clear way. The ratio of Taylor scale to system scale is a function of Reynolds number. So if we have the same Reynolds number between system, the required resolution to achieve the Taylor scale is self-similar. Likewise for Kolmogorov, the ratio of Kolmogorov length scale to system scale is equal to 1 over the Reynolds number, which means for a given Reynolds number, if we have a given resolution, the resolution required to satisfy that same fraction of Kolmogorov is self-similar with respect to vessel scale. So importantly, as we go to larger vessels, our integral scale eddies will change, but those are the ones we're already seeing so well. And even though our grid resolution necessarily gets bigger, its proportion to the overall scale is linked to Reynolds number, which means we can, even though our grid's getting bigger, as our subgrid length scales are increasing in the same manner, which means the resolution is self-similar. And so when we look at this simulation resolution here, if we're doing direct numerical simulation and capturing all the way down to the Kolmogorov scale, that will be very expensive in high Reynolds number systems with large length scales. But we're not doing that. We're doing large eddy simulation, which means in as much as we get down to the Taylor scale, we're going to be capturing the relevant physics. Things below that will be isotropic, but that's where the LES filter works best. So even though we're seeing less and less of this region over here, is the place where the filter is designed to work the best. And we can reliably predict transport inside these large scale vessels, even with a large element size. In fact, here's some papers we wrote, some results we published on this earlier this year, where we looked just at wall-bounded flow and looked at how LES compared to DNS. Yes, when we do DNS simulations and peer down in to the viscous sublayer, we can recover U plus versus Y plus, of course. When we do coarser simulations, we can't see into the wall. We can still predict buffer and integral behavior, even without seeing the sublayer explicitly. This needed a wall function to do it. But the important point is this, is that we can recover this near wall behavior. We can recover this subgrid behavior using an appropriate, even with large resolutions, because this is where LES models are designed to behave their best. Okay, so we've been alluding to this fact that simulations of LES can work, or LES simulation can work at large scale previously. I knew this talk was coming, and so I left a breadcrumb trail in one of our previous slides. You remember this when we talked about particles and residence time distribution. This, yes, is a wastewater treatment scaled on model. But if you use your imagination, it's actually a room, okay, where we have 2 vents, 2 fans, and a return duct. We're going to be adding dye through these 2 vents. It's going to be pushed around by these 2 fans and leaving through the duct here. Blue is the measured RTD, which correlated very well to what would be expected for 2 tanks in series systems. The length scales aren't quite room-like, but it's big compared to a lot of our familiar lab scale systems. And again, this is a pretty small, it's a closet, but nonetheless, you can see we're getting closer and closer to room and facility than we are to a lab scale bioreactor. So again, in this system here, we have, I'm going to use this term liberally, but I don't think I'm flawed here. It's water, not air, but that's okay. It's still a turbulent system. And I'll call these impellers fans, and I'll call these ducts. As we let the fluid come in, we can watch its dispersion. As we watch the fluid move, we can watch it advect throughout the system. As we watch the fluid advance towards the return here, we can call this event. We can predict things like an RTD and an exit H distribution. And so foundationally, yes, this is a wastewater facility, but because we're solving physics at the level of the transport carriers, and because we're appealing to conservation law, specifically conservation of mass, momentum, and energy, as it were, it doesn't matter. It could be a room. It could be air. These particles don't care what fluid they're in. What they're solving is a general transport equation that is extensible to things beyond just closed, agitated vessels. And I think this kind of illustrates that nicely. And more importantly, it serves as a test bed for validation. Blue is when measured residence time distribution in this I'll use it liberally, room-sized vessel with fans. Green is what we predict. The fact that we can nail it affirms the fact that we can indeed apply LES simulations to systems where the grid spacing is large. Why? Because the turbulent length scales are self-similar. So even though our grid space might be 10 centimeters, well, good news. The ratio of Kolmogorov to vessel size and Taylor to vessel size was self-similar across those regimes. So now, importantly, and more importantly, with respect to HVAC, these approaches scale very well with topological complexity. In fact, I can take a BIMS file directly and load it into M-Star. A BIMS file is like an architectural design file. It's what architects use to design facilities. I'll show it here. I just recorded my screen here so I could speak to this point. But in this case here, I'll illustrate this. I'm going to load in an entire BIMS assembly, right? Which has everything in it. All the room, the tables, the computers, the bioreactors, the doors, the partitions, etc. And here it is. I'm going to go ahead and clean this up a bit, but this is the actual raw architectural design file, as it were. And I'll delete to see inside. Here we can see inside the actual, this is the facility as designed. Now, this particular BIMS file, I'll randomize the color so I can see things more clearly. It has some of the original elements in there. And so if I go into this guy, I can see it's got some of these leftover walls that are going to be removed as part of this demolition. So I'll do a modicum of cleanup here. I'll go ahead and just like delete a few of these guys where the rooms are, where these walls are removed. But importantly, it's like a modicum of cleanup to take this BIMS file and take it from having some as-built features and converting these kind of existing walls here and just blast them away and getting this down to the as-designed features. Now I've got to go and specify boundary conditions. No problem. I can just group this very complex topology together and isolate the geometry that are forming the rooms. Now, I know I'm being hyperbolic here with this very complex example, but there's a point. Like if it's easy for me to navigate this system with chairs and computers than actual instrumentation, it's very easy for me to handle a very simple toy problem that's typically published in literature, as I'll speak to momentarily, guys. But there it is. There's the geometry ready to go. And we've got the full featured nature of it. Now, again, you've got to get this from an architect. If you have an architect, you can have a CAD designer make a surrogate here. But again, the salient takeaway point is this, is full complexity, full feature complexity that's in play. Here I'm defining boundary conditions. I'm going to go ahead and start selecting these events, as it were, and I'll click on them and start defining what error is coming in which one. And again, this can be wired up with a PID controller system to govern how flow moves as a function of, say, concentration or some sort of controller logic, whether it be temperature, whether it be species, whether it be CO2, etc. I can, again, specify flow rates, velocities, pressure, whatever it might be. I can specify constant time varying values. Because everything's being solved in a time-accurate manner, right? Because everything's being solved in a time-accurate manner, I can have time-varying physics within it. Again, I'll go ahead and define one more outlet here. I'll define just one because I want to get this show on the road. But importantly, you're seeing here that this problem is scaling linearly with the number of inlets. It's not like becoming increasingly difficult to add more features, right? I'm just selecting geometry, defining what's going on there, and the rest just comes, as it were. Let me go ahead and set this resolution to be something more appropriate. I'll set the return to just be a pressure boundary condition because that's where fluid's coming out. Let me go ahead and push this around, and I'll change my resolution here. But again, just my one inlet, that's all I need. But I could go through and snap these guys routinely. I'll go up here and choose the resolution. Again, I'll be modest since I'm running on my laptop. It's this example on my laptop, but it's got a 4 centimeter grid spacing, which is fine. I'll go ahead and kick this guy off. And importantly, like once I hit go here, once I kind of select this file and hit go, like we're gone. I'm exporting this mesh, which takes a bit to do, of course. It's like 100 megabytes of data, so it takes a while to export all this mesh. But foundationally, once it goes, once it's running, again, this movie is like 3 minutes long, and there's kind of a point there. The fact that I've sucked in this geometry, I defined boundary conditions, albeit just 2, did whatever cleanup I needed to do, and now I'm off and running. Like at this point, this simulation is launched, and I'll be able to see it march through time as it finishes kind of its final setup. But it's gone. I'm marching through time. I'm on my laptop. I'm a second in. I'm not running on real time on my laptop. I'm at about 33% real time because it's a pretty modest machine. But like, I'm off to the races. And there's a real point here is the fact that I went from raw BIMS geometry. Let me kind of exit that here. Raw BIMS geometry to simulation, order of magnitude minutes and hours, as it were. And I'm not peeling everything back. I have the carts, the computers, the chairs, the bioreactors, everything in there. So again, what I had here were a few vents. I went ahead and kind of after that defined all the vents. And again, it was a scale and process. It took me 2 minutes to define 2 boundary conditions. It took me 10 minutes to define 10, okay, for lack of a better word. I also have a few returns in here and a couple of workers that'll be emanating particles. And so what I get out of this then is a full fidelity model as well as a time accurate description of the fluid going through it. So this is the flow field, right? When I have all the vents going through the system. I'm not looking at a snapshot. I'm not looking at a hollowed out room. This is the time evolution of the flow field running through the system with people inside of it. Here, for example, is how we might use this. Like again, most simulations almost kind of end there. They're like, well, we got high velocity here, low velocity there. We'll send the report in and there's our consulting project. But we can do so much more. Like we're actually tracking the time evolution of these species in physics in real time. We can do things like a smoke clearing. And this is one of the biggest applications we're seeing at some of our pharmaceutical clients is they spend an inordinate amount of time doing kind of smoke clearing tests in physical spaces. Well, guys, we can do that in an hour in the GPU, on the GPUs, right? To see like where the smoke tends to linger, how long it takes for the space to recover, how we should configure our vents, as it were. Smoke testing is a big part of this qualification process, and be able to do it in silico with the as-built or as designed or possibly as-built configuration. Very compelling when that CFD simulation can run faster than probably the experimental setup. We can do other things, as it were, to kind of characterize, again, this is the smoke clearing, but to characterize not just what it looks like, but how long it takes. And in this case here, it took about, 3 minutes, 4 minutes for us to completely purge the smoke from the system, as it were, which was, this is under NDA for some of these specific applications, but I can socialize was consistent with what they mentioned and observed. And again, it's not surprising that it's right because we've been validating this thing from 6 ways till Sunday. Like when I showed that, wastewater treatment facility, like we nailed that guy. It's no surprise that if we formulate that to be have a little more complex internals and a few more vents, it's not surprising we get the right answer. We've been getting the right answer for the past 10 years. It doesn't matter whether they got now a desk and a computer inside the room. Age. I talked about age last seminar. Go back, please, and read it or watch it if you can. But this is an incredibly compelling analysis tool to use on these HVAC systems. So we talked about age, describing how old the fluid was inside different parts of the room. So here I go and I see, like again, look at the talk if you didn't see it last time, review this concept. But here I see that fluid up here tends to be the oldest fluid in the room, right? On average, the fluid here has been in the room for like 60 seconds. Compare that to fluid over here, which has only been in the room for 20 seconds, or compare fluid right near the vent that has been in the room for less than a few seconds because it just came flushed in. But here we can see where stuff tends to stagnate and hang around. Like I probably wouldn't want to keep product over here where this area isn't stagnant. That's not the right word here, but the air is certainly vintage. Let's put it that way. The air is certainly matured. We're not getting exactly the youngest, freshest molecules in the room anymore. But being able to see not just where the air goes, but how long air tends to spend and where the oldest air tends to sit and reside is useful for understanding where we don't want to put our stuff if we're trying to prevent it from being in a region where air has had a bit of time to crust, for lack of a better word. And again, we can do more than just look at it. We can study it. We can see how different venting configurations might inform both the distribution of age as well as the CDF. So I can see in this particular room here, my mean age of the air is around 30 seconds or so. Does not say there are some parts where the air is 2 minutes old, been hanging out there. A better designed process has a narrower distribution, right? And a more actively flowing process has a delta function moving closer and closer to 0. So the more this becomes a delta function, and the closer it gets to 0, or 0 implies we're just immediately voiding the room. But this variance here, I mean, I don't want to be qualitative here. It is what it is. But foundationally, this process could be improved. And I'll show how to improve it momentarily. So you've got a lot of variation in both local RTD, as well as how long air is hanging out in that room as a function of position. And this is how we can start to analyze this. So let's look at these people here and kind of see how well we're purging how this room is voiding, how this venting configuration is voiding the room. And what do I see? I see this guy is in a great spot. Like where he is, his particles are being zapped right out the room given his position. This fellow, not so much. In fact, we are achieving a certain ISO classification that may not be what we want based on this venting configuration and where this dude is standing, okay? Now, importantly, we can run these simulations, some of these, when appropriately configured faster than real time. So ideally, if we can see a guy is here standing, we can run that simulation, see how it's adjusting, and say, hey, you better get out because we're seeing that our particle count might achieve unacceptable levels. Move, get out, or stand near your vent. Or more importantly, let's change your venting configuration. But again, going back to the original point, is this multi-physics simulation is in play. Like we're not taking some mean flow field and throwing particles on there and seeing how long it takes to drain. We're actually watching these particles be dynamically emitted. We're watching these particles be dynamically ejected, and watching these particles leave the system dynamically to see what sort of particle counts and the distributions we get as a function of person count, person duration, person degree of gowning, and venting configuration. Pretty neat, as it were. It allows us to make apples to apples comparisons to what the standards expect us to achieve in terms of particle count. And here's where I talked about better designing of these vents and configurations. So again, here I've got 4 different vents to illustrate which ones are good and which ones are bad. So let's look here at vent 4 and vent 5. These are great vents because when molecules come in through them, they clean out and go. Vent 4 is great. Look at that. Nice one-dimensional flow. Vent 4 comes in, vent 4 cleans, vent 4 exits. Vent 5 isn't even that bad. Vent 5 comes in, does a little scrub-a-dub there in the corner, and then leaves, as it were. Vent 10 and vent 8 are problems, okay? Vent 8 and vent 10 are just like pushing air around. Vent 8 isn't so bad. It's doing a little bit of scrub over here in the corner, then voiding. Vent 10 is a problem. If there was an undesired species here, vent 10 is going to spread it through the room, okay? And so what's neat here is like, this is kind of like a nice another way of looking at age and velocity, is seeing where is species carried. We can see vent 10, boy, if there's a contamination, vent 10 is going to do a great job of getting it everywhere, okay? Vent 4 and vent 5 contain, vent 8 does a decent job. Vent 10, we got a problem. This coloring didn't seem to come through in the slide for whatever reason. I apologize for that. This is our removal CDF. This is vent 10. It's taking upwards of 4 minutes for vent 10 molecules to leave. And on their way, they muddied their tracks all over the facility. Vent 10's a problem. That's something that can be hard to see experimentally, as it were, but it comes up immediately when you got simulations like this. And again, beyond just like, the vents, we can model the process. I showed this before. Here are the vents for a different lab scale system we modeled. Here are the people, how they might be informing the flow. We can see like we're getting great flow through that area there. We're getting stagnation on this side over here. But again, the salient point is this. It's not just a snapshot. We're modeling the people moving. We're modeling what they do. Here they're going to go over here and kibitz and talk about, what's going on in life. We're actually seeing like how their presence, how the dynamics in tandem with the fluid flow ultimately inform what's going on inside the space, which is kind of cool. It's way beyond just a snapshot of a flow field and towards an actual dynamic process simulation. We're actually watching these people do their work and seeing how that informs. That guy's cooling off there in that nice breeze. And this guy kind of exited. He's off to lunch. And they don't walk. We didn't add the complexity where their legs are walking. They're all kind of mummies. So they're kind of like just, I don't know, moving around like they were in some sort of sarcophagus. But you get the point. We can make them walk, but that's really obnoxious and it's probably not necessary. Either way, I digress. But this goes on and on and on and on and on. Like, and I mean this point, like it is straightforward for us to model hours, should we need to, of process mechanics. And we don't need to go that long. Oftentimes, tens of minutes is sufficient to look at a purge or say how an OR might behave. But foundationally, this is in play. Okay. We've been talking so far about particles, age, flow rates, etc., turnover, mixing foundationally. We can also include creature comforts such as pH. I'm not pH, sorry, that's the wrong word. If you're concerned about pH in your house, you probably should move. I mean, like things like humidity, RH, I should say, as well as temperature. So we've talked about this previously, okay? We wrote a paper on this earlier this year, or published earlier this year, and I gave a talk about this a bit at APS DFD last fall. So I'm going to be appealing to some of these heat transfer mechanics. And again, one thing I want to emphasize here is because we're modeling physics at the level of the transport carrier, because we're modeling the dynamics using first principles modeling approaches, it becomes easy for us to generalize these things to other types of systems. Said again, when we develop a heat transfer module, as it were, we're doing it in a way that appeals to boundary layer theory and turbulent mechanics. And as a happy consequence of that, that model is then extensible to a very wide variety of systems. We're not limited to a bank of heating coils. We're not limited to a cylinder in cross flow, as it were. When we're appealing to first principles, generalized approaches, they can be used for, drum roll please, computers, heating up a room and advecting thermal energy away from them. They can be used to model humans emitting thermal energy and how that heat is removed from them and convected into the room to inform their overall temperature. And so foundationally, the spirit of M-Star is generalized first principles models that lead to generalized first principles modeling approaches that require little reparameterization and tuning between setup, which means everything we learn from the vessels, as we can validate here, conveys to the rooms. So what this looks like in action, again, this is a vessel, but use your imagination. This is a room with a fan, as it were. And so foundationally here, I've got these walls heating up. I've got advection at this wall here. I'm sorry, convection at the wall. I have conduction through the walls as a particular vessel heats up. I've got advection of the thermal energy throughout the fluid, as it were. But foundationally, whether it's a vessel, whether it's a room, we write physics that are general across these operating conditions, which means we can use these same well-validated physics that we apply to processes and apply them to facilities hosting these processes as well. There's a lot going on here. The fact that we have conduction, convection, advection, there's a lot going on, but importantly, it's all built into the code and self-consistent and all happening in tandem. So if I have temperature going into the fluid and have that fluid becoming less dense, as it were, due to buoyancy, or I have a viscosity change in the fluid due to change in temperature, that's all self-incorporated, right? I can immediately see how temperatures can inform density, maybe inform viscosity, et cetera, and inform the solution of our Stokes equations. I'm not layering on a temperature field on top to a fluid field, as it were. I'm solving all these physics in tandem and in play, which is quite compelling, I think. Okay, and importantly, just to reemphasize this point, these heat transfer approaches are surprisingly general. We talk about this ad length and probably ad nauseum in the paper, so I invite you to read that, or we can have a sidebar to talk about this in more detail. But when we use first principles modeling approaches, we can correctly predict convective heat transfer coefficients over several orders of magnitude. That is, whether it's pipes, coils, bundles, walls, cylinders, etc., we can use one approach to rule them all. Why? Because it's first principles and appealing to turbulent boundary layer theory. And when we use those types of approaches, we can extend them to a wider variety of topologies, say a heating element inside of a room. Let's now apply this to an HVAC system, okay? So we've got, or rather, a heating and cooling system. So I found a neat paper here that talked a bit about, how we can use inline, I said wireless controllers to measure temperature variations across a room and compare them to some CFD simulations. And so these authors, they have a notional room here where they have people and computers and windows and lights, as it were. They have a pretty oversized AC unit, I'll say, at the top there that's keeping this room nice and cool. Then they went ahead and measured what the temperature was at various positions, right? Which is kind of neat. And so they're measuring all this temperature field, they're measuring all this velocity field, and they're measuring how the temperature converges towards a well-defined steady state value. And so they've got here, this was the CFD data, but they did have some measured data as well. And again, this is good results, and this is generally the state of the art. It's useful in the sense it gives you some idea about temperature profiles, but we can do better. We can look at the fluctuations. We can look at how the temperature is evolving in time. The steady state results are useful and good. I don't mean to dismiss them, but we can go so much further when we have the ability to run the time macro three-dimensional simulations and be able to study how the flow physics is evolving over time. Let's go. So we were given some of the relevant data here. So let me go ahead and convert their picture into an actual process. And I'll play this just the first like 200 seconds here just so you can see what's going on. But here's what the actual process looks like, right? We've got the vent, and I in this room, it's not my business to speak to the quality of the design, but I would not be person two. You're probably going to catch a cold having air just blowing on your head all day. I hope they rearrange the chairs, but either way, I digress. But foundationally, we're moving away from just a snapshot into the actual process mechanics. Like here is the evolution of the flow field. We have the 45-degree jet of the air conditioner coming down. Again, buoyancy is included in here. We see impacting the table and whatnot. We see the recirculation. We see the return. And here is the time evolution of the temperature field. Again, I haven't yet finished the simulation yet. I'm just showing the first 2 minutes here. But I can see this combination between heat coming off the people and computers and lights. I see this cool jet coming down, getting warmed up as it comes on in. I see the time evolution of the other spaces as well, as they see different sorts of the effects of mixing as this cool air comes in, cools off the space, competes with temperature sources from the walls and windows, etc., to see how this eventual process converges. And let me go ahead and scale I'll run like the full simulation here where we have the temperature conversion. We'll show that momentarily. And I'll do my best to play these. But here is, I think this is like maybe 1,000 seconds, which isn't a big deal. I'll speak to that momentarily. But like here's the actual process whereby the room achieved the target value. And again, it took about 1,000 seconds. It takes a while to get there. You can kind of see this eventually converging to a steady state behavior as time goes on. Here is the velocity. The velocity is never steady state. It's always just quasi-steady because it's turbulent flow. But eventually the room does reach a steady state condition where the mean temperature is converged to a well-defined value, and we have a thermal balance. Now, a couple points here. One, I'll just play the side view here. It took about 1,000 seconds. That's not a big deal. That's in play. That's just a few hours of runtime. Said again on my laptop, is that these long-term processes where we're coupling tens of minutes to hours of flow simulation with a millisecond time step informing the eddy, the creation, the destruction, the advection of individual eddies, like breaching those timescales, that's in play on a GPU, right? Looking at how the temperature evolves, how the initial splash of cool air competes with the initial temperature and the ongoing thermal convection from the people and the computers, etc., and watching how it eventually cools off over this 1,000-second interval, that's in play. Like our ability to, and that's kind of one of the most important points, just as a sidebar here. People ask, I'll just kind of editorialize quickly. They'll ask a question, they'll say, what's the biggest thing you ever simulated? As if that's like some like feat. Like modeling big things isn't hard. Like you can go in Excel and model the Earth orbiting the sun. And that's a big thing, okay? But that's not hard. What makes simulations hard are aspect ratios in space and time. A simulation is hard, quote unquote, when you have a 1 millisecond time step that's being advanced for an hour, okay? And you then have to do, you know, 1 million plus time steps. A simulation is hard when you have high spatial disparities, say small features, say a caster of a wheel on a chair inside a 10-meter diameter room. Simulations are hard when the aspect ratios are great, but that's precisely where tools like this shine. Like it can comfortably handle the 10 million time steps required to simulate an hour of process. It can comfortably handle the 100 million lattice points required to achieve the resolution necessary to see the computer keyboard on the table in the room that's 20 meters long. Like that's where these type of GPU approaches shine, because in doing so, you don't have to simplify your model and do like, well, here's a mean flow field. We'll slap some particle tracers on there and see how it goes. Because you can bridge these timescales, you can model the millisecond eddy time scale with a 10-minute particle resonance time, or I should say cooling time scale, as it were, all within one simulation to watch these guys get coupled. And again, here we can see this process occur. Like it took, again, a solid 10 minutes to achieve the target steady state temperature, which was measured, of course. We can see how that evolves over space. And importantly, see how temperature is distributed. I didn't show the time evolution of the temperature PDF. That might have been interesting to watch how it kind of cools down and evolves. I just showed the final value here, showing the PDF and CDF. And again, seeing that, 99% of the room is below some target temperature, and above some target temperature as well, which is both need to be considered in this particular application. Both min and max need to be considered explicitly. But again, I'll emphasize this point. This wasn't like, oh, let's predict a mean flow field and then throw a temperature solver on this. This is all these tens of minutes and hours of long simulations are happening in tandem in a multi-physics manner that allow us to bridge the link between eddy timescales and process outcomes. So that again, there's like a incredible view here that comes. We can understand how the individual eddies that arrive in decay over a fraction of a second ultimately inform the several thousand second process outcome. That's neat when you have a holistic view into process mechanics. Now, importantly, because we're solving these physics in real time, as it were, we can model feedback control. Now, I've spoken about this in a few seminars. I'll just have one movie to speak to this point. But here is a notional lab scale system. And one of these guys I showed earlier as part of our talk, where I've got some workers in a lab space, subject to an unfortunate leak under their hood. I'm going to pause it here. There is feedback control. I have sensors throughout this system that are measuring the concentration of this gas. When that concentration exceeds a critical value, the control logic vents the room, as it were. Now, importantly, all of these physics are embedded, right? I'm not looking at a mean flow field, and then turning it into a RTD, then putting it into a MATLAB PID controller to figure out the response time. I'm modeling all these physics in tandem and in real time. So eventually we get to the probe where we sense this undesirable concentration. And then what does the system do? It responds by purging the system. Here it comes. You can actually see the people moving. I got to give my credit to Johannes for actually having the people move. It's incredible what he did with that. But here we watch the room venting in response. And so the flow rate of these gases is responding to controller logic. Right? As the concentration becomes more acceptable, this flow rate goes down. As the room begins to recover, it's more its target state. But importantly, folks, so I'll go ahead and look at this from a side view here. And I'll have the most realistic part of the simulation is this guy here standing there looking at his phone the whole time. So here you can look at him. He barely even nudges because there was a really cool thing that came on Instagram right at this moment. But here we've got the concentration going up with the probe. And eventually the PID system's responding by venting. And here we have eventually these guys are responding. It goes through the roof because the signal gets too high. We're maxing it off flow rate, as it were. Eventually the signal's getting to an acceptable level. The flow rate's going down. At the end of a minute or so, we recover back to where we needed to go. But again, here's the point. We're solving this all, the controller logic, the species transport, the fluid flow is all being solved in tandem. Again, I'll admit that the people moving, that's just kind of gilding the lily. That's just kind of getting excited there. But it's pretty cool to watch kind of all these physics. Like watching that guy crouch, like it's actually terrifying to watch him crouch. But at the end of the day, like we can model how his crouch informs the fluid flow, which is pretty cool. And that guy, again, he's back to his phone. They're just crouching. Let me go ahead and show one more view of this here. So here's kind of the side view here, watching again, these people respond in response to the fluid leaving, watching this happen in real time. Here we see just the vents above the operators here. We were saving volumetric data pretty aggressively to make this nice rendering, of course. And you can go back and see Johannes's talks on how to give good renderings like this. These guys respond, the vents come on. This guy can't even be bothered, which I think is kind of funny. But at the end of the day, the important point is this. When you can bridge these time scales, bridge these length scales, a lot of interrogation comes into play. We can see how the venting configuration, the PID controller, and the operator response ultimately informs the time evolution of concentration. We can integrate these into one model to rule them all, which I think is really compelling. Okay, let's end with some conclusions, and then I see a couple questions came in, and please populate with questions so we can speak to them. This idea of time accurate LES simulation for larger scale systems is routine. Okay, this isn't like a speculation or some idea that we might try this. Like people are doing this. We are publishing on this. We are validating these tools, as it were. it is practical to simulate hours of flow. In some applications, we can simulate days of flow, as it were. This is made possible by GPUs, codes that run on GPUs, and GPU enhancements in GPU architectures that present us as code developers with a large number of CUDA cores and a very large cache of memory and the attendant high memory bandwidth. These problems scale very well with complexity. You saw me earlier go ahead and build this system using a raw BIMS file. That was kind of a dog whistle because folks recognize that a lot of simulation involves trying to simplify the geometry to make it practical and palatable for simulation. We're moving in the opposite direction. We're able to take the exact as-built or as-designed model, suck it in, and run with it, okay? This has important implications for us as CFD engineers. One, it minimizes our cleanup responsibility. And two, it maximizes the fidelity and faithfulness of our model. Said again, if we're reducing our system to a square with a box bioreactor and a box guy and a box desk, as it were, it's a bit more of a sell to convince our facility manager that this is what he's actually looking at. It was looking at is actually the room. But if we can take the as-built system, we can load that right into the model and run with it. It's immediately recognizable to the facility designer what's going on in the simulation. In fact, I'll just kind of pull on this thread once more. Simulation is abstract. Simulation is abstract, but the more we can make it recognizable in terms of the space, the dynamics, the flow, the topology, etc., the more understandable it becomes to people that may not be simulation experts. So again, it is easy to model complexity, and it is easy to make these things multi-physics. Adding temperature fields, as it were, to look at, say, buoyancy or looking at how temperature evolves for the system, easy. We've been doing that for years. Adding controller logic to see how the actual Emerson PID loop is going to inform whether it be temperature, concentration, purging, etc. That's straightforward. And this is really kind of like a incredible view where you can see how the timescales of the eddies interact with the timescale of the flow rate of the vent, interact with the purging timescale or the residence time of the fluid, interact with the PID controller timescale to produce some sort of aggregate system performance. Like when you have that holistic view and can see how all these physics are interplay and are interconnected, it's very compelling to see, oh, what if I just change the vent? What if I change this, the PID feedback control? What if I change the position of the return, as it were? When you can make these adjustments without having to rip the guts out of your model every time, you become very efficient from a process simulation standpoint and a CFD engineer. Next steps, including real-time data is becoming in play, where we can actually give the code insights at runtime to inform the trajectory. Like, think about this here. We have our simulation running, just running in the background. Maybe it's even running at real time, as it were, in the multi-GPU environment. We then want to know, oh, Bob came in and he coughed. Okay, hopefully Bob doesn't cough. But at the end of the day, like, what's the consequence of that? We can begin to model those perturbations, model those shocks to the system in real time to see how it's going to respond in real time and what we might need to do, how we might need to diagnose or fix the system. And that's really cool because as we start to achieve parity or even acceleration with respect to real time in our simulations, we have a real digital twin that allows us to interrogate the system, to shock the system, and see how it's going to anticipate how it's going to respond to aberrations. This can be generalized to other types of flows. If there are questions on that turbulent self-similarity, I'll speak to it again. That's a very complex idea to pack into 3 slides in 10 minutes when I'm talking about Komarov and Taylor. We can speak to that in more depth today in our questions and answers or if we're in a sidebar. But foundationally, the self-similarity of turbulence flows means this is generalizable to other spaces, and we're seeing some of this. So beyond facilities, folks, we have folks doing dam breakage. We have folks doing now, river flows, as it were, because foundationally, the self-similarity of the turbulent mechanics paired with LES simulation allow this model to be extensible, not just from lab scale, not just to production scale, not just to pilot, I should say, not just to a facility, but actually to an environment. And that's a really cool next step that comes in generality of the simulations. Thank you. I hope you see kind of how these concepts stitch together and how the generality of these modeling approaches apply not just to a shaken flask, but to a hospital, and to a manufacturing facility. When we build physics that are foundational, the models become self-similar. Thanks again. I'm happy to take any questions. I think we have a few that came in. We got a few minutes to speak to them. But yeah, thanks again for your attention, your time, and for being here.
Yeah, first question.
Yeah, and let me know what you got. Let me know what you got.
Is the NVIDIA 4500 ADA card compatible with M-Star?
Great question. The only requirement we have is that your compute capacity greater than 3.5, which means the GPU has to not be more than like 12 years old, okay? The compute capacity defines what sort of logic the GPU can host, whether it can do certain floating point operations or whatnot. GPUs from like 2010, 2012 may not have the appropriate compute capacity. So just look at it. And again, I don't know, there are so many NVIDIA GPUs. I don't know the specs of the exact one, but assume the last 5 years, I'm sure it's fine. Now, bear in mind though, running is good, but you have to look at the number of CUDA cores and memory bandwidth. The size of the GPU in terms of memory informs the number of lattice points that GPU can host. The number of CUDA cores on the GPU inform how fast it'll run. So ideally, you want a simulation with lots of memory and lots of CUDA cores. Now, I don't know what the ADA 4500 has, but just be mindful if the simulation will run on it. But if it's undersized, you might see some performance issues. But yeah, assuming it's something over the last 5 years, you should be good to go. Great question.
Okay.
Great question.
Next question is about slide 32. PDF and CDF of which quantity was plotted? Is PDF and CDF directly available as output from simulation, or user needs to calculate them based on the simulation data?
Great question. Funny you should ask. As of yesterday, you can calculate PDFs directly in M-Star and have that output. This was generated as a post-process exercise. But if you're reading your M-Star updates, your nightly M-Star updates, like some people read their morning newspaper, you will see that in runtime, histograms are now part of M-Star. So I can generate this at runtime and watch it evolve at runtime. CDFs are the next step. That's coming in the immediate future because they're a simple extension of the PDFs or an adjacent extension of the CDFs. But so I did this in post, but to be sure, by the time this video is available to the general public, this will be it already is a built-in feature in M-Star. The CDF will be as well.
Okay. How could we set up a simulation to run on a GPU instead of a CPU in OpenFOAM, for instance? And the second part of that question is, does the DLSS feature available in NVIDIA GPUs have any impact on the processing speed or performance when running CFD simulations on the GPU?
I'm not an OpenFOAM expert. I don't run OpenFOAM. I'm not familiar with getting OpenFOAM to work on GPUs. This is all with M-Star CFD. What I do know is this: is M-Star is born and bred and designed to run on GPUs. Maybe someone else can speak to OpenFOAM. I don't know if OpenFOAM is important to GPUs, but I do know this, and I'll make this point. It's like there's a big difference between getting something to run on a GPU and having to run well on a GPU. I made this claim, and I'll argue it again, that a good GPU has a functional compute capacity that is hundreds of times as hundreds of times the compute capacity of a CPU. So if you're running on a CPU and running a GPU and your code doesn't increase in speed by a factor of 100 or several hundred, as it were, you're not taking full advantage of that GPU. So running on a GPU is like, it's a moral victory. You've got to be able to exploit it. Like I can put a spoiler on my Kia and call it a race car, but it's not, okay? And so foundationally, I don't know how well OpenFOAM does on GPUs or run on CPUs. Maybe you can shoehorn it in there with some of these libraries. I'm not sure. But foundationally, if you want to exploit all the promises of GPUs, you've got to use code that's born and bred to exploit those internal calls explicitly, is my understanding. Am I answering that? Hopefully I'm answering that question okay, but that might be a sidebar, but just because it runs on the GPU doesn't mean it's running well, okay? Or realize any of the promise that what the GPU offers.
Okay, 2 more questions. Can M-Star provide more toys to aid in seeing setups, to aid in setting up our own models? Maybe not necessarily all the controller logic, but basics.
Oh yeah, M-Star has lots of toys. Like if I go over here, there are lots and lots and lots of templates you can use to kind of watch these things go on and kind of see how they do. There's lots of like toys built in. And if there's a specific toy, we can snap one together to kind of illustrate this. That toy model's one now. But yeah, there's a lot built in now, and a lot more that we can kind of ship as part of the documentation.
Okay, you mentioned environmental applications with M-Star. What kind of simulations were you referring to?
I was referring to external channel flows. I was referring to large wastewater treatment facilities. I was referring to environmental flows where we have, length scales on the order of hundreds of meters, as it were. I'm referring to lagoons, as it were, wastewater lagoons, those types of scales. Those are in play now.
Okay, last question. How do I get the M-Star updates? I could answer that. It's on the documentation page, the main page. You can tell them, John.
Downloads to M-StarCFD.com. Downloads to M-StarCFD.com. That'll get you where you need to go, and you can download the latest nightly build.
Okay, great. Well, I think we're almost out of time here.
Yeah.
Sorry. One other. Oh, there's a few other questions, but what do you think, John? Should we try to answer them?
Yeah, I can see them.
Okay.
Heat transfer capability through having an object moving through an oven. Yes, of course. We've done that before. We've done that with cars moving through an oven to model the curing of paint. They'll have the oven move over the car just to kind of make it easier to model the conduction grid. Different GPU card impact simulation time and cleaner simulation. Very simple rule. More CUDA cores, faster runtime. Period. More GPU RAM, larger simulation. That's the answer. Guys, we're at time. Email me if any questions come up. We'll take it from there. Thank you so much for your great attention today and great questions. Appreciate you being here. Thank you.